Hello everyone, welcome back. So let's talk about those Hume-Rotheby rules. Okay, now there are cases where we can have, atoms. Okay, here's our atoms. And we can take a similar atom and just kind of like, okay, nothing to see here, just kind of put it in there. Now this is a substitutional solid solution when it's able to just take any spot at once and nobody's the wiser. And some metals are really, really good at that, but not all. So let's look at these three situations and see which of these might be able to have this complete solubility. So let's work through it. So chrome and vanadium. Now to be able to solve these problems, you're going to have to look at some tables in your book. And one of the things you want to find are the following. You want to find the radius, their atomic radii. You want to find their crystal structure. You want to find their electronegativity. And you want to find their valence. You need to know all of these things. Now for chrome, it's 0.125, and that's in nanometers. It's a BCC structure, 1.6 electronegativity, and it's got +3 valence. Vanadium, 0.132, BCC, 1.5, and it's usually +5, but it can also be +3. And then our Hume-Rotheby rules will compare all of these. So first off, I gotta see what is the percent difference between the radius. So 0.132 minus 0.125 over 0.125. This is how you do percent difference. It's what you get at the end minus what you had at the beginning, divide by what you had at the beginning, or just, you have one on both. So, you have the difference over one of them. This will be around 6%, depending on which one you do. The structures are the same, which is good. The electric negativities are very comparable, that's good, and their valence is also the same. And with that, these would be able to be a solid solution. But what am I talking about here? Well, one, to be a complete solid solution, they have to have similar radii. So the difference should be about less than or around about 10%. Second, they need the same structure. They need similar electronegativities. And also similar valence. If they have all of these things, then they can be a complete solid solution. In this case, all four of these are met. They had a very similar radii, similar structure, the same structure, similar activity, and the same valence. Okay, so chrome, vanadium, they would be a complete solid solution. Now, how about magnesium and zinc? Okay, magnesium, zinc, radii, and once again, you're going to have to look these up in your book. I magically know them because I'm your teacher, but you might not, and that's okay. You're not expected to memorize these. Okay. And what do we have here? Well, we got 0.160 and 0.133. Hexagonal close packed for both of these. Electronegativity of 0.1.3 and 1.7. And finally, valence of +2. Now, if I look at the percent difference here, so 0.160 minus 0.137 over 0.137 times 100, that is going to be around about 17%, depending on which one you do. That's too big. Too big. It needs to be roughly less than 10%. I mean, 11% can work if everything else is perfect, but you want to be at 10% or less. And so this is way too big. So we already know this isn't going to work. They got the same structure though, that's good. Same valence. Their electronegativity is also fairly different. It's not terrible, that could still work if everything else was fine. So the primary reason these would not be a complete solid solution is just that one of them is too big. Too big. Okay. Let's look at the last one, which is aluminum and zirconium. So we have aluminum right here and zirconium. And we have our radii, structure, electronegativity, and valence. So we have 0.143 and 0.159, FCC, and hexagonal close pact. 1.5, 1.2, plus 3, plus 4. Now, if we're doing the percent difference, it'll be around 11%. That's not perfect, but that can kind of, we'll give it a check minus. That can almost work. Their structures are not the same. FCC and hexagonal close pact, they kind of look similar if you're looking at how they're stacked. And they do have the same packing efficiency, but they're not the same structure. There is some difference between their electronegativities. This is not perfect. And the valences are fairly close. But because of the structure, that's the biggest issue for us. They would not be a complete solid solution. Okay, so 3 examples, and I've walked through all these Hume-Rotheby rules. Remember, similar radii, same crystal structure, similar electronegativity, and similar valence. All these need to match for them to be able to have a complete solid solution. Well, that'll be it for now. Thanks for watching. I'll see you all next time. Bye-bye.